In a previous video, I talked about antenna coverage patterns and reading antenna coverage graphs. In this video, I'm going to talk about a different aspect of antenna signal propagation, and that's polarization. We can think of signals coming out of an RF antenna similar to ripples on the surface of water when a rock is thrown into the water. An electrical current moves through the elements of the antenna, and whenever electrical current moves, an electromagnetic field is set up. And this is the exact same principle that occurs if you ever did the experiment as a kid where you wrapped a nail in some wire and then you put a battery on the wire and you turned it into an electromagnet. Well, it was also a very untuned, very bad antenna, that nail was. It was creating an electric field. The difference there in that example and our example is that that was probably DC current, and DC current isn't very useful for communicating information because it just sets up the magnetic field and then the magnetic field doesn't do anything. So when we're doing RF transmissions, we're going to be using AC current, which means that the electromagnetic energy is going to move up and down, back and forth, and that's what makes the waves. If we look at this illustration, we can see that the RF signal is made up of an electric and a magnetic field, and they are oriented at 90 degrees to each other. And we define the polarization of the signal as the orientation of the electric field. The orientation of the electric field, or the polarization, is going to be a physical characteristic of the antenna. So for example, if we have a dipole antenna, the physical construction and design of that antenna means that it emits the electric field oriented in the same direction that the antenna is oriented. So if the antenna is pointed straight up and down, then the antenna will have vertical polarization. The electric field will be oriented straight up and down. If we lay the antenna on its side, it'll be the other way around. And as we rotate the antenna through potentially 360 degrees of rotation, the polarization would similarly rotate. So it is a physical characteristic of the antenna that results from the design of the antenna. Now we talked about the dipole or omnidirectional antenna here, and it's very intuitive to think about the polarization of a dipole antenna because it's straight up and down, you have vertical polarization. It's on its side, you have horizontal polarization, or anything in between. If you have a directional antenna, it will also have a polarization, but it will not necessarily be as obvious what the polarization is. And a directional antenna will typically have a little arrow imprinted on it or marked on it, painted or something that will indicate the polarization direction based on the antenna's orientation. Okay, so that's how you know the polarization there. Now, polarization matters because when two antennas are polarized exactly the same, maximum energy is transmitted between them, and that's good because when you want to receive a signal, you want to receive as much energy as possible. So in this case, we have two antennas that are both vertically polarized. One transmits energy to the other, and there is minimal or potentially 0 dB of loss between them. And likewise, if they're horizontally polarized, as long as they're both horizontally polarized, and likewise for any sort of degrees of polarization in between. We could tilt these antennas to any angle as long as they were both tilted to the same angle, they would have same polarization and you would get maximum energy transfer between them. And of course, that's what we want. The worst case scenario for this type of polarization is if the two antennas are 90 degrees out of polarization with each other. And what that means is that one antenna's electric field is aligned with the other antenna's magnetic field and vice versa, and that means they don't interact very strongly at all. And you'll get a lot of loss in that case, as much as perhaps 25 or 30 dB of loss, which is quite substantial if you're not sort of intuitively familiar with dB. That's a lot of loss. So your goal should be to always have your linearly polarized antennas aligned with each other as much as possible. And that's easy to do if you're mounting your antennas on the side of a building, but it's a little hard to do if your antenna is in an airplane or a quadcopter. You may have your antenna on your transmitter standing straight up and down, and you may mount the antenna on your copter or your plane straight up and down. But as soon as you take off, now you've pitched forward, you've rolled to the left, you've rolled to the right, and the polarization may not line up. And that is why we often see receivers with diversity. Well, there's several reasons why diversity is a good thing. But one of the reasons is that it helps you compensate for changes in polarization. Diversity means that the receiver has two antennas, and at any given time, it listens to the antennas, and whichever one is giving it the strongest signal, that's the one it pays attention to. And if the strongest signal comes in on the other one, it moves to the other one. So it basically doubles the chances of getting a good, strong signal. Now, if we were to take these two antennas and just put them right next to each other, let's say we just taped them together in some heat shrink so they were literally right next to each other, you can see that the diversity wouldn't really have any positive effect because they both would be receiving basically the same signal at the same time. What we do with diversity is we take these two antennas and we put them 90 degrees to each other. And what that means is that if a signal is coming in that is cross-polarized with one antenna, it will be perfectly polarized with the other antenna. So if we imagine these antennas, one of them pointing straight up and down and one of them aligned with the horizon, then whichever way the signal comes in, vertically or horizontally polarized, it's going to line up with one of those two antennas. And that's where diversity helps us. Now, the worst case scenario is if a signal came in aligned 45 degrees to the horizon, at which point it would be equally out of polarization with both of them. And that's the worst case scenario. So that's still way better than if it was 90 degrees out of polarization, completely cross-polarized. So what we've done with diversity, if you set your antennas up correctly in a 90-degree orientation, which you should always do, if you do that correctly, then you're minimizing the worst case scenario that can happen with regards to polarization, and that's a good thing. Now, diversity helps by reducing the negative effects of cross-polarization. But you may remember from the last video that these antennas also have a coverage pattern that is going to affect the strength of the signal they receive. And it can be very confusing to people who are new to this topic that polarization and the coverage pattern are completely different things. So if we go back here, if we go back here, if I start rotating this antenna in a circle, I am going to change the polarization of the signal, but I'm also going to be rotating that coverage pattern that I showed you in the previous video. And so I'm also going to be, remember I said that there was a very, very weak spot at the very top and the very bottom of the antenna, and that maximum signal reception was edge on to the antenna if this was a dipole, right? If this was a directional antenna, then we would have a weak spot behind the antenna and a very strong spot out in front of the antenna, okay? Let's treat it as a dipole, though. If this was a dipole, we'd have a weak spot at the top and the bottom, and as we rotate this antenna, we're moving where those weak spots are. So, for example, if you're standing at the flight line on your flying field and your antenna is pointing straight out into the field, not only you may be sending vertical or horizontal, you've changed the polarization by the orientation of the antenna, but also you're sending the strongest part of your signal straight up into the sky and the weakest part out into the field. Okay, so we change both polarization and the sort of aim of the energy, the focus of the energy based on the antenna's coverage pattern when we change the physical orientation of the antenna. And that comes into play here in this diversity setup. Imagine a scenario where a signal is coming in from this direction. Now that signal may be out of polarization with this antenna. Let's say the signal is cross-polarized with this antenna. So that means it's perfectly polarized with this antenna. Now that cross-polarization may cost us 30 dB of loss on this antenna. But because we're in the null at the tip of this antenna, we're coming in from the worst possible direction, that may cost us 40 dB of loss because we're in the weak part of this antenna's pattern. So we may actually get a scenario where the cross-polarized antenna is actually stronger than the antenna that's correctly polarized because the signal's coming in on the weak part of the correctly polarized antenna's pattern. So the takeaway from this is that this 90-degree orientation on your diversity antennas is the best alignment to maximize the chances that you're going to get a strong signal, but it doesn't necessarily compensate for every possible combination of polarization and antenna pattern. And you could always get some worst case scenario that's going to cause maybe as much as 30 or 40 dB of loss. And that's significant because if you're in a sort of a best case scenario where everything is lined up perfectly, you're correctly polarized, and you're in the strong part of the antenna's coverage pattern, you could get fantastic range. And then when you turn the copter, you're in flight, maybe you turn the copter so you're in a less optimal scenario, then suddenly you're in the worst case. So if you're going to do range tests, definitely make sure you do range tests at many different, turn the copter all different directions, etc. Walk around it, and definitely try all sorts of orientations that might occur. And you can sometimes see a pretty substantial change in signal strength based on different orientations of polarization and where you are in the antenna's coverage pattern. Now, so far we've been talking about linear polarization, which can be pictured like this, and that linear polarization can be vertical or horizontal or anything in between. But there's another thing, and that's called circular polarization. And again, circular polarization, it's a little hard to conceptualize, but you can imagine if linear polarization is a waveform sort of going up and down in a plane, circular polarization can be imagined as a waveform sort of corkscrewing out from the antenna. And the reason that circular polarization is beneficial is that circular polarization is independent of the orientation of the antenna. So you can say if my antenna is straight up and down, I'm putting out this corkscrew. But as I continue to rotate this antenna through 360 degrees, right, the corkscrew is the same. I mean, I'm just putting out the same corkscrew anyway, right? So circular polarized antennas are relatively independent of their orientation when it comes to polarization. You can have the antennas oriented basically any way you want, and there's no polarization loss. Whereas with linear antennas, if they are oriented 90 degrees to each other, there's as much as 30 dB of polarization loss. So that's a good thing. Also, circular polarized antennas are better at dealing with something called multipath, which I won't go into. But that's one reason why circular polarized antennas are commonly used for FPV video. There's a good question here, and that is, why aren't circular polarized antennas commonly used for control? And I don't actually know the answer to that, but they're not. So there you go. With circular polarized antennas, the antenna can either have left-hand polarization or right-hand polarization, which you can just imagine the corkscrew going the other direction. And in the same way that we want our linear polarized antennas to be aligned with each other, you want to have your circular polarized antennas consistent, either left-hand or right-hand. You'll get, again, as much as 30 dB of loss if you cross-polarize your circular polarized antennas. But they're not sensitive to orientation. Well, actually, be careful there. Circular polarized antennas are not sensitive to orientation when it comes to polarization loss, but they still have that same dead spot at the top and bottom of their coverage. If we're talking about an omni, like a cloverleaf antenna, they still have that same dead spot in the top and bottom of their coverage, just like a dipole or a linear polarized antenna would. That's a different factor, though, than the polarization loss. So with circular polarization, we can safely bank the copter over, turn it upside down, whatever, and we will not get that 30 dB of polarization loss. And this, by the way, may be one reason why it is not common to see diversity, not as common anyway, to see diversity on FPV stuff. When you do see diversity on FPV, it'll be because usually you've got one omni antenna for up close and one directional antenna for far away, as opposed to diversity with linear systems where you'll have two of the same antenna at 90 degrees to each other. We're going to close up here with just an overview of various combinations and their associated loss. Same polarization, linear vertical, linear horizontal to itself, or left-hand or right-hand circular to itself, 0 dB loss. That's obviously the best case scenario. Any cross polarization has 25 to 30 dB loss. You can actually use this to your advantage. If you're doing FPV, you can take pilots on alternating frequencies and have them alternate left hand, right hand, left hand, right hand to keep them from interfering with each other. But your equipment needs to have all left hand or all right hand, or you won't get any range. And then finally, any circular to any linear has a fixed 3 dB loss. This can actually be a good thing. You could have a circular on your headset, on your goggles, and a linear on your copter, and it will mean that you'll be less sensitive to orientation than if you had two linears. But obviously, the best case scenario is two circulars. You would only do that like if you broke your cloverleaf or something. But this is an okay thing. It's not terrible. All right, well, that's it. and happy flying.